Hello everyone, welcome to week 3 of the Diffusion Seminar. Today I'll be presenting Generative Modeling Part 2, following up on last week's session, Generative Modeling Part 1. In this talk, we'll take a closer look at the variational autoencoder and introduce the foundations of denoising diffusion probabilistic models. Last time, we explored the variational autoencoder where an input image X is passed through a probabilistic encoder that outputs mu and sigma. Based on this, we sample a latent vector Z, which is then passed to the decoder to reconstruct the image. This forms the basis of VAE training framework. We saw that the objective of VAE is to approximate the true data distribution by maximizing the evidence lower bound, ELBO. The ELBO consists of two terms: a reconstruction error, which encourages to accurate image reconstruction from the latent variable, and a regularization term, also known as the prior fitting term, which ensures that the learned posterior stays close to the prior distribution. So how does the VAE actually optimize this ELBO objective in practice? Then how are the VAE model and diffusion model related? Today we'll explore the mathematical foundations underlying this line of inquiry, including likelihood, maximum likelihood estimation, maximum a posterior, and variational inference. Then we'll delve deeper into the VAE, examining its optimization process and sample generation. Finally, we'll provide an overview of DDPM, denoising diffusion probabilistic models. First, likelihood measures how well a statistical model explains observed data by calculating the probability of seeing that data under different parameter values of the model. In simpler terms, likelihood tells us how probable it is that a given model could have generated the observed data. The key point here is that the parameters of the model are treated as variables, and we assess how likely the observed data is given those parameter values. Likelihood and probability are often confused concepts. To clarify the difference, let's take a closer look at how they differ. Likelihood measures how well our model explains the observed data. It is interpreted by reading the probability density at the observed data point. In the example shown, the likelihood evaluates how plausible it is that data point X was generated by our model and assigns it a value of 0.24. In this setting, the model parameters theta are typically the variables we aim to estimate. In contrast, probability refers to fixing the model parameters and varying the expected event, computing how likely that event is to occur under the model. This is done by integrating the probability density function PDF over the event region. In the given example, the probability of a certain event occurring under our model is 0.21. The probabilistic method for estimating the parameters that maximize this likelihood is called maximum likelihood estimation, MLE. MLE aims to find the set of parameters that maximize the likelihood of the observed data under the model. In fact, all generative models, whether explicit or implicit, fundamentally aim to maximize the likelihood of the observed data. In the example below, among the candidate models, the one whose probability density function is shown in orange, assigns the highest likelihood to the observed data points. However, MLE also has limitations. Since it maximizes the likelihood based solely on the observed data, it is prone to overfitting, meaning it can tailor itself too closely to the specific dataset it was trained on. Consider the table below as an example. If we flip a coin 10 times and observe 10 heads and 0 tails, then the model that best explains the observed data under MLE would assign a probability of 1.0 to heads. Likewise, if we observe 8 heads and 2 tails, the MLE solution would be 0.8. However, in reality, we often have prior belief, for instance, that coins are typically fair. If we take such prior knowledge into account, a more reasonable or robust estimate might assign a 65% chance of heads rather than fully trusting the limited observed data. The process of incorporating our prior belief into parameter estimation is called maximum or posteriori estimation, or MAP. Unlike MLE, MAP evaluates how plausible a parameter theta is after observing the data based on both the likelihood and a prior belief about theta. In other words, instead of just asking what parameters best explain the data, MAP asks, given the observed data, which parameter values are most likely, considering both the data and our prior knowledge. We begin by expressing the posterior using Bayes' rule. Since p of x is constant with respect to theta, we can ignore it during optimization. This leads to the following MAP objective. So, MAP maximizes the product of likelihood and the prior. In MAP, what we aim to maximize is the posterior p of theta given x. This posterior consists of the numerator, which includes the likelihood p of x given theta, and the prior p of theta, which encodes our belief about the parameters before seeing the data. And the denominator px, known as the evidence, which is constant with respect to theta and thus ignored during optimization. Returning to the coin flipping example, when we incorporate our prior belief, the parameter can be estimated using MAP, which yields the following result. What is the relationship between MLE and MAP? If we carefully examine the formulas for MLE and MAP, we can see that when the prior term p of theta is a uniform distribution, it becomes a constant with respect to theta. In that case, MAP becomes equivalent to MLE because both are maximizing the same likelihood term. Okay, so let me wrap up by summarizing the key differences between MLE and MAP. MLE does not incorporate prior belief, whereas MAP explicitly does. Because of this, MAP can help mitigate overfitting by guiding parameter estimation with prior knowledge. However, it is important to note that both MLE and MAP are point estimation methods. They provide a single best guess for the parameters without accounting for uncertainty in the estimates. So why is uncertainty important? First, for reliability. When a model can express its confidence or uncertainty, its predictions are more interpretable and trustworthy, especially in high-stakes domains like medicine or autonomous driving. Second, for sample diversity. In generative models, explicitly modeling uncertainty allows us to sample diverse and realistic outputs, rather than collapsing to a single deterministic solution. Now let's move on to variational inference VI. While MAP aims to maximize the posterior and thus yields a point estimate, VI seeks to approximate the full posterior distribution over the parameters or latent variables. In this sense, VI is a distributional inference method, not a point estimation method. One key difference is that unlike MAP, VI cannot ignore the evidence term in base rule because it does not simply search for the parameter that maximizes the posterior. Instead, it aims to approximate the entire shape of the posterior distribution. However, this integral term, the evidence, is generally intractable. Why? Because the integration is performed over theta, which is typically a high-dimensional continuous variable, making the exact computation of the marginal likelihood px analytically infeasible. So far, we've looked at variational inference from the perspective of Bayesian parameter inference. To prepare what comes next, we'll now switch the notation to focus on latent variable inference. From this point on, instead of estimating the parameter theta, we'll focus on inferring the latent variable z. This shift is crucial as latent variable inference lies at the heart of models like VAEs and diffusion models, which we will explore in details moving forward. In variational inference, we approximate the intractable true posterior by introducing a tractable distribution Q of z given lambda. Instead of directly working with the true posterior P of z given x, which is often computationally infeasible, we define a simpler parameterized distribution Q and optimize it to be as close as possible to the true posterior. In this setup, lambda represents the variational parameters, that is, the parameters of our surrogate distribution Q, which we will optimize during inference. This process is equivalent to minimizing the KL divergence between the two distributions. This KL divergence term can, by definition, be expanded as follows. And using the rules of logarithms and the definition of expectation, it can be rewritten as the difference of two expectations as follows. Let's summarize up to this point from the Bayesian rule. This expression can be rewritten using logarithmic rules as follows. And as a result, the term inside the final expectation can be taken outside, removing the expectation. We have expanded the expression starting from the KL divergence all the way to the final term. Let's keep these two components in mind as we continue the derivation. By isolating the term log p of x from the two expressions, we arrive at the following form. Since scale divergence is always greater than or equal to 0, we can therefore establish the following lower bound, which is known as the ELBO or evidence lower bound. If we further expand the ELBO using Bayes rules and the definition of scale divergence, we ultimately arrive at the following expression. In variational inference, we typically assume that the true posterior P of z given x is fixed but intractable. Thus, maximizing the ELBO becomes equivalent to minimizing the posterior gap, the KL divergence between the variational distribution and the true posterior. There is also a variant called amortized variational inference, AVI. Instead of optimizing a separate set of parameters, lambda, for each individual data point, AVI introduces a parametric model phi that learns to predict lambda directly from the input x. In this way, we avoid the need to optimize a large number of separate lambdas and instead train a single shared model that amortizes the costs of inference across all data samples. Alright, now we are fully ready to dive into variational autoencoders, VAEs. Unlike standard VI, in VAE, the true data distribution is approximated by a decoder, while the posterior distribution is inferred through an encoder. This process is amortized, meaning we use a neural network to map each input x to an appropriate latent variable z. As a result, the VAE objective is to optimize the ELBO, which we saw in the previous session, and it takes the following form. So then, how do we actually optimize the ELBO in practice? We begin by making two key assumptions. First, we assume that the output of the encoder follows a multivariative Gaussian distribution. This assumption is deeply embedded in the architecture of the VAE itself. Specifically, the encoder is designed to output the mean mu and standard deviation sigma, which define the parameters of the approximate posterior Q of z given x. Second, we assume that the prior P of z follows a standard multivariate normal distribution. This prior encourages the latent space to be centered and isotropic, making generation and sampling more stable and tractable. Let's first take a look at the first term of the ELBO, commonly referred to as the reconstruction term. This expectation can be expressed as an integral, and we estimate this term using Monte Carlo techniques. Monte Carlo techniques or Monte Carlo estimation refer to the method of approximating expectations when direct integration is intractable. Instead of computing the integral analytically, we sample multiple z values from the distribution and compute corresponding values of p of x given z, then average them to approximate the expectation. Now let's break down the expression. Suppose we further assume that p theta of x given z follows a Gaussian distribution. Then the log term becomes the log probability density of a sample drawn from a normal Gaussian distribution. Using the formula for a normal Gaussian distribution, this expression can be rewritten as follows. By simplifying this once more, we arrive at the following expression. In this expression, the second term can be treated as a constant if sigma is assumed to be the identity covariance matrix. As a result, only the first L2 loss term remains, which is why this part of the ELBO is commonly referred to as the reconstruction term. Secondly, what if p theta of x given z follows a Bernoulli distribution instead? In this case, the log likelihood term can be decomposed into a sum over dimensions, assuming conditional independence of each pixel given the latent variable. By logarithmic identity, this product becomes a sum, which ultimately leads to the familiar binary cross entropy laws used for reconstruction when modeling binary data. Now let's take a look at the regularization term. This term is actually straightforward to handle because both distributions involving the KL divergence are assumed to be multivariative Gaussian distributions. As a result, there exists a closed form expression for the KL divergence between them. By applying this closed form expression, we can expand the KL divergence term accordingly, which leads us to the following formula. And this makes the term straightforward to compute. Now we are ready to optimize the ELBO by combining both terms. However, there is a challenge. When constructing the ELBO, we use Monte Carlo estimation, which involves drawing stochastic sample of Z. This introduces randomness into the computation graph, making gradient-based optimization problematic. For example, suppose we want to compute the gradient of the ELBO with respect to the mean mu by the encoder. This requires applying the chain rule where we need the gradient of z with respect to the mu. However, since z is sampled stochastically, the gradient term becomes undefined, making the propagation through the sampling operation infeasible. So the VAE addresses this issue in a clever way. But before we diving into the solution, let's take a brief look at an earlier workaround proposed in other research. Due to time constraints, today we'll focus specifically on the reinforced trig, also known as the log derivative trig. First, the expression we want to differentiate is as follows. This term, according to the definition of KL divergence, can be rewritten as follows. The expectation term can be decomposed as follows. Using the definition of expectation and applying Leibniz rule, we obtain the following expression. By additionally applying the product rule, the expression becomes like this. In the second term, the parts involving theta or prior can be ignored during differentiation. Then, by applying the log derivative rule, we arrive at the following expression. By simplifying this expression further, we get the following form. And finally, by applying the log derivative rule one more time, we can rewritten the expression as follows. At this point, the expression becomes equivalent to applying Monte Carlo after fixing z, which means the gradient can now be computed, making the entire process differentiable. However, this log derivative trick, though useful, has a major downside. The gradient is computed as a product of two terms, the first being what we'll later refer to as the score function, and the second being the reward or loss term. When multiplied, these two terms can result in high variance, which can lead to unstable training and slow convergence. Instead of using the log derivative trick, VAE enables differentiation by splitting the sampling process into two steps, a technique known as the reparameterization trick. The idea is simple. First, sample an epsilon from a simple distribution such as a standard normal Gaussian. Then use this epsilon to construct the latent variable z. If the approximate posterior q phi of z given x is Gaussian, then z can be constructed as like this. This formulation is mathematically equivalent to sampling z directly from the encoder output, but now the randomness is isolated in epsilon, allowing gradient to flow through mu and sigma. If we visualize the reparameterization trick, we see that epsilon becomes the only stochastic node, while mu and sigma remain in the computational graph, enabling backpropagation. Okay, so this is how the VAE is optimized. To summarize, given an input image, we train VAE by reconstructing that image, optimizing the ELBO, which consists of two key components, the reconstruction term and the regularization term. In order to allow gradient to flow back through the encoder, we apply the reparameterization trick, which enables the backpropagation through the stochastic sampling process. This completes the full optimization pipeline of VAEs. During inference, thanks to our modeling assumptions, we can draw an epsilon from a standard normal Gaussian, use it to construct z, and fit this z into the decoder to generate a new image. This is how the VAE functions as a generative model. Now, finally, let's take a brief look at DDPM, the denoising diffusion probabilistic model, which can be considered the starting point of modern diffusion models. DDPM addresses some of the core limitations found in VAEs. VAEs suffer from two major issues. The latent prior is too simplistic, typically a standard Gaussian, which may not capture the complexity of the data distribution, and posterior collapse, where the encoder stops producing meaningful latent variables because the decoder becomes too powerful. In ELBO optimization, if the decoder is overly expressive, it may learn to ignore the latent variable entirely, effectively collapsing the posterior to the prior. This undermines the purpose of learning a meaningful latent representation. A notable work that addresses this issue is WikiVAE, which you may want to read further. These issues often lead to poor quality generated images, a problem that DDPM successfully addressed. Like the VAE, DDPM is also a latent variable model, but it approaches generation and inference in a fundamentally different way. If we think of the VAE encoding process as the forward process and the image reconstruction from the latent as the backward process, then diffusion models follow a similar structure. However, the key difference is that in the forward process, diffusion models gradually add noise to the data. This added noise becomes the latent representation, which DDPM treats as the central objective modeling. So just as the VAE optimized the ELBO, DDPM also optimizes an ELBO, but here it treats the noisy image at time step t as the latent variables. The training objective is structured similarly. DDPM defines a probabilistic generative process and maximizes a corresponding ELBO over the diffusion trajectories. The most important aspect of DDPM is that it models the diffusion process as a Markov chain, where Gaussian noise is gradually added over time. As shown in the equation below, the Markov assumption states that the latent at any time step t depends only the latent from the previous step t-1, meaning each step is conditionally independent of all earlier steps given in the immediate previous one. DDPM assumes that the transition from one step to the next follows a Gaussian distribution. At each time step t, a new noisy image xt is sampled from a distribution condition on xt-1 according to the Markov chain formulation. The amount of noise added at each time step is controlled by a variance schedule beta t, which gradually increases over time. The key point is that the forward diffusion process can be expressed in a single step. In other words, given the original image at step 0, we can directly sample the noise image at any arbitrary time step t by sampling from a known distribution. Specifically, xt can be sampled from a closed form Gaussian condition on x0 using the cumulative noise schedule. We'll explore the details of this formulation in the next session on DDPM. Another important point is that if the forward process is Gaussian, then the reverse process is also Gaussian. We'll revisit this idea in more detail in 2 weeks during the seminar session where we interpret diffusion as statistical differential equation SDE. Therefore, the process of starting from the latent and gradually recovering the original image is equivalent to estimating p theta of x given z. In DDPM, this corresponds to a step-by-step backward process, where at each step, the model predicts the previous noise image from the current one, as shown in the equation below, using a Gaussian distribution for each transition. So how can we optimize this procedure? Next week, we'll take a deep dive into DDPM, focusing on its mathematical foundations, the training objective, and the sample generation process. Then, in the following week, we'll shift to viewing DDPM through the lens of stochastic differential equations, SDEs, which will lead us more advanced methods such as DDIM and DDPM solver. Thank you for listening to my presentation. I hope you're looking forward to the next week's seminar as well. Thank you.